Space is expanding. Galaxies are drifting farther apart. Ancient light is stretching across the dark. But a quiet question remains. If space itself is growing, what is it growing into? There is no wall at the edge, no empty room outside the cosmos, and no center where everything began to fly away. The answer is stranger, calmer, and deeper than it first appears. Stay with this journey into the shape of space, and if this kind of slow cosmic documentary helps the night feel quieter, like the video and subscribe to the channel. At the farthest reach of observation, the universe is known through light that arrives after crossing immense stretches of space. This outer region is not an edge that can be touched, and it is not a border with another place beyond it. It is the limit of what can be seen from one location in the present age of the cosmos. Every telescope, whether on Earth or above Earth's atmosphere, receives signals from objects and fields that have already sent their light long ago. The farther the source, the older the light. The visible universe is therefore a sphere of arriving information, centered on the observer only because the observer stands at the place where the light is received. Another observer far away would have a different visible sphere, with the same laws of physics and a different set of farthest signals. This outer observable region is shaped by time as much as by distance. Light moves at a finite speed, so it cannot bring news from every part of existence at once. Space may continue beyond the visible region, but no signal from those farther places has had enough time to arrive. Observations indicate that the universe is about 13.8 billion years old, but the farthest visible regions are now much farther away than 13.8 billion light-years. This is because space has expanded while the light has been travelling. The light begins its journey when the universe is smaller and denser, and during its long passage, the distance between large regions grows. By the time the light reaches observers, the source region can be far beyond the simple travel time of the light itself. This makes the outer region difficult to imagine with ordinary experience. On Earth, expansion usually means a thing growing into surrounding air or water. A cloud expands into the atmosphere. A ripple spreads across a pond. A balloon swells into a room. These images are useful only for a short distance, because they bring along an outside space that already exists. Cosmic expansion does not require that kind of outside. At the observable edge, what is being measured is not a surface moving into another region. It is the changing distance between places within the universe itself. The outermost visible light does not show a wall. It shows that space has carried distant regions away from one another while the light was on its way. The light from the most distant galaxies is stretched by this expansion. Its waves grow longer as space grows between the time of emission and the time of arrival. This stretching is called redshift, because visible light shifted toward longer wavelengths appears redder. Though much of the distant signal can move beyond visible light entirely. Redshift is one of the central signs that distant galaxies are not merely flying through a fixed emptiness. Instead, the scale of space between them and the observer changes over time. The farther the galaxy, in the broad pattern of the universe, the greater the stretching of its light tends to be. This pattern is not perfect for every individual object, because galaxies also have their own local motions, but across great distances the relation is clear. Near the edge of observation, galaxies appear as they were when the universe was young. Their light carries records of early star formation, early chemical enrichment, and early structure. Some appear small and irregular compared with many nearby galaxies. Some shine strongly because young stars are forming rapidly within them. Others are seen through the help of gravitational lensing, where gravity from closer matter bends and magnifies their light. Even in these remote views, the same point remains steady. The telescope does not look toward a physical boundary. It looks backward through layers of time, toward a universe whose light has taken nearly the whole age of cosmic history to arrive. The word observable is important. It does not mean all that exists. It means all that can be known through signals that have reached the observer so far. Beyond the farthest arriving light, the universe may continue with more galaxies, more empty regions, and more large-scale structure. It remains uncertain how far the whole universe extends beyond what can be observed. The observed evidence supports a universe that is very large and nearly uniform on the largest scales that can be measured. Nearly uniform means that, when averaged over enormous regions, matter and radiation are spread in a similar way in all directions. This does not erase galaxies, clusters, or voids. It means that the widest pattern has no known special edge or central place. At this outer level, the question of what space expands into begins to soften. It comes from the habit of imagining space as a substance inside a container. Observations point instead to a universe in which the container idea is not needed. Distances inside space change. Light records that change. Galaxies show it through redshift. Ancient radiation shows it through its cooling. The outer visible region is therefore not a rim pressing into a larger darkness. It is the farthest layer from which information has arrived. The sky itself gives this lesson quietly. In every direction, deep observations reveal distant objects, faint light, and old signals. No direction shows the universe opening into a surrounding room. No direction points to a central explosion site. The expansion appears as a relation among distant places, not as motion away from a single outer boundary. The farther regions do not show the cosmos bursting through a shell. They show space stretching the paths of light. This outer observable edge is also limited by the early state of the universe. There is a time before which ordinary light could not travel freely through space. In that earlier period, matter was hot and dense enough that light scattered again and again from charged particles. The universe was not transparent in the way it is now. For this reason, ordinary telescopes cannot see back through that bright early fog using visible light alone. The farthest direct light comes from the moment when the universe becomes transparent, and the signal from that time now arrives as a faint microwave glow. Even this glow is not an edge in space. It is a surface in time, a record of when light begins to move freely across the universe. At the outermost observable region, the mind meets a boundary of information rather than a boundary of existence. The universe does not present a final wall, a last galaxy, or an exterior into which everything spreads. It presents arriving light, stretched wavelengths, ancient signals, and distances that have grown while the signals moved. The scientific picture remains careful and restrained. Observations show expansion within the universe. They do not show an outside space receiving it. The farthest visible light is therefore the first quiet clue that the question may need a different shape. Space is not seen expanding into something at the edge. Space is seen expanding by changing the distances that make the edge visible at all. Beyond the farthest galaxies that can be studied in detail, the idea of a cosmic horizon becomes the next outer region. A horizon is a limit to what can be received, not a hard surface in space. It is similar only in a loose way to the horizons seen across an ocean, where the curve of Earth hides what lies farther away. In the universe, the cosmic horizon is made by the age of the cosmos, the speed of light, and the expansion of space. It marks the distance from which signals can have reached one observing place by the present time. It is therefore a boundary of knowledge, not a boundary of matter. This horizon surrounds every observer, from Earth. It appears in all directions because light arrives from all directions. From a galaxy far away, its own horizon would surround it in the same way. No observer sits at a privileged center of the whole universe by having a horizon around them. The horizon is local to each point of view. It forms because information travels through time. A signal from too far away has not yet had enough time to cross the growing distance. The region may exist, but it remains outside direct contact. It cannot be seen, measured, or used to define an outer wall. The word horizon helps describe several related limits. One is the particle horizon, which is the farthest distance from which light could have reached an observer since the beginning of the hot, expanding universe. It is a record of all regions that have been able to send signals so far. Another is the event horizon, which applies in models where expansion continues in such a way that some signals emitted now from very distant regions will never arrive. These horizons are not objects. They are relationships between light, time, and geometry. Geometry means the measured structure of space and time, including distances and paths. At this outer layer, the expansion of space changes the meaning of distance. A distant galaxy can now be so far away that the space between it and an observer grows faster than light can close the gap. This does not mean the galaxy moves through nearby space faster than light in the ordinary sense. It means that the distance between widely separated regions increases because the scale of space changes. The local rule remains intact. Light always passes nearby observers at the speed of light. Across enormous distances, however, the total separation can grow in a way that places some regions beyond future communication. The cosmic horizon therefore does not behave like the edge of a room. A room has a wall, and beyond the wall there may be another space. The horizon has no thickness and no material surface. It is not a shell that galaxies strike or cross in a physical sense. As the universe ages, the region from which light has had time to reach observers can change. Some old signals arrive for the first time. Other regions, because of continuing expansion, may become unreachable in practice even though their earlier light remains visible for a while. The horizon is a moving limit in the history of observation. At great distances near this horizon, light is strongly redshifted. Its wavelengths have been stretched by expansion across long periods. Energy that once may have been carried as visible or ultraviolet light can arrive as infrared or microwave radiation. The signal becomes faint, not because it passes through an outer barrier, but because its energy is spread and shifted during the growth of space. The brightness of distant sources also fades because the light spreads across a larger area, and because the rate at which arriving waves are received is slowed by the same expansion. Distant events appear to unfold more slowly, since the intervals between arriving wave crests and signals are stretched. The horizon also shows why the universe can be larger than the part that is visible. A person standing in a fog sees only a limited region, but the fog does not prove that the world ends at the distance where sight fails. In cosmology, the limit is not ordinary fog at the present time. It is the finite travel time of light and the earlier opacity of the hot young universe. Observations can infer much about the universe beyond direct sight, only by using patterns within the visible region and by applying tested physical laws. Still, direct evidence stops where signals stop. Scientific language must remain careful there. It can say what observations indicate within the visible universe, and it can describe possible larger forms, but it does not turn the unseen beyond the horizon into a known landscape. This careful boundary is important for the question of expansion. If the horizon were a wall, it might be natural to ask what lies on the other side of the wall, but the horizon is not the edge of space. It is the edge of accessible information. The universe does not need to expand into a region beyond the horizon, because the horizon is drawn inside the universe by the observer's past light cone. A past light cone is the set of places and times from which light could arrive at a given event. It is a structure of communication, not a container. The horizon also has no center in the ordinary sense. Every observer can place themselves at the middle of their own observable sphere, because received light comes inward from all directions. This center is observational, not cosmic. It is like hearing sounds from every direction and mapping them around the listener. The map is centered on the listener because the listener receives the sounds. It does not follow that the listener is the center of all space. In the same way, Earth is central only to Earth's observable universe, not to the universe as a whole. Near the cosmic horizon, the ordinary habit of imagining an outside becomes less useful. The horizon is not something into which space expands. It is something created by expansion and finite light travel. The farther the light has travelled, the more the expansion of space has affected its path and wavelength. The horizon is therefore one of the clearest signs that the universe must be understood from within its own geometry. The limit is not a place where space ends. It is a limit in the history of signals. The calm picture is one of distant regions, delayed light, and a boundary that belongs to observation. There is no observed outer surface. There is no known exterior pressure or surrounding emptiness into which galaxies move. The cosmic horizon simply marks the farthest reach of contact so far, and that reach depends on the age and expansion of the universe. What lies beyond it, if anything can be described by that phrase, is not an outside room around the cosmos. It is beyond present observation. The horizon remains a quiet line in knowledge, drawn by light itself. Inside the horizon of observation, the next region is the broad field of expanding distances. This region is not marked by a surface, but by a pattern. Across very large scales, galaxies and groups of galaxies tend to become farther apart as time passes. The space between them changes its scale. This does not mean every object flies through space from one central point. It means that the measured distance between widely separated places grows when the universe is described as a whole. The expansion is therefore a change in the arrangement of distances within the universe, not a motion into another surrounding place. The simplest way to hold this idea is to imagine many distant regions placed across a wide, even field. When the scale of the field grows, the spaces between the regions grow with it. Each region sees many far regions becoming more distant. No one region has to be the center. The pattern looks similar from many locations because the change belongs to the scale itself. In cosmology, this scale is described by a scale factor, a number used in mathematical models to show how distances between far, unbound regions change with time. The term is technical, but its meaning is plain. It measures the growth of cosmic separation. This expansion appears through the light of galaxies. When light travels across growing space, its wavelength is stretched. A wavelength is the distance from one crest of a wave to the next. As the wavelength grows longer, the light is shifted toward redder colors or beyond visible light. This red shift is not only a change in color, it is a record of how much the universe has expanded during the light's journey. A galaxy whose light has a larger cosmological redshift is generally being seen from farther back in cosmic time. The observed pattern shows that distant galaxies are, on average, carried into increasing separation from observers by the expansion of space. The relation between redshift and distance is one of the foundations of modern cosmology. Nearby galaxies can have motions of their own that disturb the pattern. Some move toward one another because gravity pulls them within local groups and clusters. But across larger distances, the general trend becomes clear. The more distant the galaxy, the more its light is stretched by cosmic expansion. This does not show a blast wave moving through empty surroundings. It shows that the distances inside the cosmic fabric have changed while the light has crossed them. The word fabric can be helpful only when used gently. Space is not a cloth floating in another space. It has no woven surface that can be seen from outside. The word points instead to geometry, the way distances and paths are arranged. In general relativity, gravity and motion are described through the geometry of space and time. On cosmic scales, the geometry can change with time, and the change appears as expansion. The galaxies are not all moving through a fixed background as sparks through air. The background distances themselves are part of what changes. This is why expansion is often described as separation without ordinary motion. Galaxies still have local motion through their surroundings, and they still respond to gravity. But the large-scale increase in distance is different from a rocket crossing space or a stone thrown through the air. The space between far regions grows. An observer in one galaxy can see another distant galaxy's light stretched, and an observer in that distant galaxy would see the first in a similar way. The effect is mutual because it arises from the shared expansion between them. This also explains why there is no need for an outer room. If distance itself is changing within the universe, then the expansion is not a movement of the universe into pre-existing emptiness. The usual image of an expanding object comes from daily life, where objects sit inside larger spaces. Bread rises inside an oven. Steam spreads into a room. Smoke expands into the air. The universe, in the scientific model, is not treated as an object placed inside a larger container. It is the whole setting in which distances are measured. Its expansion is a change in that setting. The pattern becomes clearer when the attention stays on very large scales. Galaxies are not sprinkled evenly like fine dust at every distance. They form groups, clusters, sheets, and long threads, with wide empty regions between them. Yet when the universe is averaged over enormous volumes, it appears close to the same in every direction and from every place within the observed region. This large-scale sameness is called homogeneity when it refers to place, and isotropy when it refers to direction. Homogeneity means no large region is known to be special when averaged at the greatest scales. Isotropy means the universe looks broadly the same in every direction. Together, these ideas allow the expansion to be described as a general scaling of distances rather than a flow away from one center. The expansion also affects time in observations. Distant events appear slowed because the intervals in their arriving light are stretched. A burst that lasts a certain time when emitted can be received over a longer time after crossing expanding space. This is not because the distant event itself is slow in its own local surroundings. It is because the light carrying the record of that event has been stretched along with space. The same process lengthens wavelengths and lengthens the observed timing of signals. The universe leaves the mark of expansion in both color and rhythm. At this region of the topic, the question of what space expands into becomes a question about what kind of thing space is. If space were a material cloud inside a larger chamber, then expansion would require a chamber. But observations and general relativity point to a different description. Space is not known as a substance with an outside surface. It is part of the geometry of the universe. When the universe expands, the geometry changes so that large distances increase. There is no observed outer boundary where new space pushes against something beyond it. This does not mean all distances grow. Bound systems resist the general expansion because other forces dominate within them: gravity, electromagnetism, and the strong forces inside matter hold smaller structures together. The broad expansion is seen between far regions that are not bound tightly enough to remain together. At this scale, the universe behaves like a changing map, whose grid spacing grows over time. The map is not printed on paper outside the cosmos. The map is only a way to describe the relationships within it. The region of expanding distances is therefore quiet and precise. Galaxies mark the pattern. Light carries the evidence. Redshift reveals the stretching. The large-scale universe increases its separations without pointing to an outside place. Expansion is not the universe moving into a surrounding void. It is the growth of distance within the universe itself, measured from inside by observers who receive ancient light and compare it with the light of nearer worlds. Within the broad field of expanding distances, the next inward region is the ancient light that fills the observable universe. This light is known as the cosmic microwave background. It is not light from stars or galaxies. It is a cooled remnant from a time when the universe changes from being opaque to being transparent. Opaque means that light cannot travel freely because it is repeatedly scattered. Transparent means that light can move across space without being constantly interrupted. The cosmic microwave background is therefore a record of an early state of the universe, carried across expanding space until it reaches observers as a faint glow from every direction. This ancient light begins its free journey when the universe is much younger, hotter, and denser than it is at present. Before that time, ordinary matter exists mostly as a plasma, a state in which electrons are not yet bound to atomic nuclei. Free electrons scatter light again and again, so photons, the small packets of light energy, cannot travel far in a straight path. The universe is filled with radiation, but it is not transparent. As expansion continues, the universe cools. Electrons and nuclei combine to form neutral atoms, mostly hydrogen and helium. With far fewer free electrons in the way, light begins to travel freely. That released light becomes the cosmic microwave background. This region is not a distant shell in the ordinary sense. It is often pictured as a surrounding surface because the light reaches observers from every direction, and because all of it comes from a similar early time. Yet the surface is a surface of last scattering, not a material wall. Last scattering means the last time those photons are strongly deflected by charged particles before they travel freely. The light is observed as coming from far away because it has travelled for almost the whole history of the universe. The places from which it last scattered are now extremely distant, but the meaning is temporal as well as spatial. It marks a stage in cosmic history. When this light first travels freely, it is much hotter than it appears now. Its wavelengths are shorter, and its energy is higher. During the long passage through expanding space, the wavelengths are stretched. As the wavelengths grow, the radiation cools. By the present time, it has become microwave radiation, far colder and less energetic than visible light. The glow has a temperature of only a few degrees above absolute zero. Absolute zero is the lowest possible temperature in physics, the point where thermal motion reaches its minimum allowed state. The background is cold now because space has expanded by a large factor since the light began moving freely. The cosmic microwave background is nearly uniform across the sky. In every direction, its temperature is almost the same. This deep sameness is one of the strongest pieces of evidence that the early universe was hot, dense, and smooth on large scales. Yet it is not perfectly uniform. Tiny differences in temperature appear across the sky. These differences are very small, but they matter greatly. They reflect slight variations in density and motion in the early universe. Over time, gravity acts on these small variations, helping matter gather into the later large-scale pattern of galaxies and clusters. The background, therefore, preserves both smoothness and the seeds of later structure. At this layer, the expansion of space is visible in a particularly direct way. The ancient light is stretched into microwaves not because it loses energy by rubbing against a substance or leaking into an outside region, but because the space through which it travels grows. Each photon remains light, moving locally at the speed of light, but its wavelength increases with the expansion of the universe. This is the same broad process seen in the redshift of galaxies, carried to an older and more universal signal. The entire background glow is a cooled record of expansion. The cosmic microwave background also helps define what is meant by seeing outward as seeing backward. The light now arriving from this early time does not show the universe as it is now in those far regions. It shows the universe when the light last scattered. Those regions have continued to evolve during the long travel time. Matter there has formed structures under gravity, just as matter in the observable region has done elsewhere. The background is therefore not a present-day wall. It is an old image of a young, transparent surface in every direction. This distinction keeps the idea of expansion grounded. The ancient light does not come from an edge into which the universe expands. It comes from a time when light first becomes able to cross the universe freely. When observers map it, they map a spherical view because they stand at the receiving point of photons that have travelled inward from all directions. A different observer elsewhere would receive a different sphere of ancient light, centered on that observer. The background is universal in the sense that it fills space, but each observation of it is centered by the act of receiving the light. The glow also shows that the universe has no known preferred direction at the largest observed scales. Its near uniformity supports the idea that the broad universe has the same large-scale properties in every direction. Small corrections are needed because Earth, the Sun, and the Milky Way move relative to the background. This motion creates a slight warming in one direction and cooling in the opposite direction, a pattern caused by motion through the radiation field. Once this local motion is accounted for, the background becomes an even more precise record of early cosmic conditions. This early light is measured by instruments above Earth's atmosphere and by careful observations from the ground. Space missions have mapped its temperature differences in detail. These maps do not reveal a cosmic exterior. They reveal a young universe with small density variations, a universe whose radiation has been stretched by expansion and whose matter later gathers under gravity. The evidence supports a universe that expands from a hot, dense, early state, not an explosion into surrounding emptiness. The word explosion can mislead, because explosions happen at places inside space. The early universe is not described as matter bursting from one point into empty surroundings. It is described as space itself being hotter, denser, and smaller in scale everywhere in the observed region. The cosmic microwave background sits at a special inner boundary of sight, not at the outer boundary of being. Ordinary light from earlier times is blocked because the universe is not yet transparent. Other forms of evidence, such as the abundance of light elements and the behavior of early fluctuations, help describe earlier periods, but direct ordinary light stops at this surface of last scattering. This limit is again a limit of observation, not a hard edge. It tells where light last interacted strongly before travelling freely. In the calm glow of the cosmic microwave background, the question of what space expands into becomes even less like a question about walls and more like a question about history. The glow has cooled because the universe has expanded. Its waves have lengthened because distances within the universe have grown. It arrives from all directions because the early transparent universe surrounds every observer in the form of ancient light. It does not point toward an outside. It points toward a time when the universe becomes clear enough for light to cross it, and that light still carries the slow, stretched memory of expansion. Moving inward from the ancient background light, the universe begins to show its large-scale structure in clearer form. This structure is often described as a cosmic web. It is not a web in the sense of threads laid within a surrounding space. It is a pattern formed by matter under gravity within an expanding universe. Galaxies gather into clusters. Clusters link into elongated filaments, and between these structures lie vast regions with relatively little matter. This arrangement emerges over billions of years as small early variations grow under the influence of gravity, while the overall expansion continues. The cosmic web reveals that expansion does not erase structure. Instead, it provides the stage upon which structure develops. In the early universe, matter is nearly uniform, with only tiny differences in density. Over time, slightly denser regions attract more matter through gravity. As they draw in surrounding material, they grow denser still. This process continues, forming the first bound structures. Filaments arise as matter flows along preferred directions shaped by the initial variations and by the geometry of space. Nodes form where filaments intersect, becoming the locations of massive clusters of galaxies. Between these filaments and nodes are large voids, regions where matter is less concentrated. These voids are not completely empty, but they contain far fewer galaxies than the denser regions. The web-like structure spans immense distances, far larger than any single galaxy or cluster. When observed across sufficiently large scales, the pattern appears statistically similar in different directions and from different locations. This supports the view that the universe is homogeneous and isotropic when averaged over the larger scales, even though it is highly structured on smaller scales. The formation of the cosmic web is influenced by both gravity and expansion. Gravity pulls matter together, encouraging the growth of clusters and filaments. Expansion, on the other hand, increases the distances between regions that are not strongly bound. These two effects operate together. In dense regions, gravity can overcome the expansion locally, allowing matter to collapse into bound systems. In less dense regions, expansion dominates, stretching space and increasing separations. The resulting structure is therefore a balance between attraction and expansion, shaped over long periods. Dark matter plays a crucial role in this process. Dark matter is a form of matter that does not emit or absorb light in a way that can be directly observed, but its presence is inferred from its gravitational effects. It provides much of the mass that drives the formation of the cosmic web. Observations indicate that dark matter forms the underlying scaffolding of the universe's structure. Ordinary matter, such as gas and stars, follows this scaffolding, collecting in the potential wells created by dark matter. The web seen in galaxy surveys reflects this deeper distribution. As the universe expands, the large-scale pattern of the web remains coherent. The distances between major structures increase, but the structures themselves persist. Filaments stretch across greater separations, and clusters move farther apart from one another. This does not mean the web is being pulled into an external space. The pattern evolves within the universe, with expansion changing the scale while gravity shapes the details. The web is therefore an expression of how matter organizes itself under known physical laws in an expanding geometry. Light from galaxies within the cosmic web carries information about this structure. By measuring the positions and redshifts of many galaxies, astronomers map the three-dimensional arrangement of matter. These maps show long chains of galaxies, dense clusters, and wide voids. The redshift of each galaxy provides an estimate of its distance, allowing the structure to be reconstructed across vast volumes. The pattern that emerges is consistent with theoretical models based on general relativity and the presence of dark matter. The cosmic web also evolves over time. In earlier epochs, the structure is less developed. As time passes, gravity amplifies the initial variations, making filaments more pronounced and clusters more massive. The expansion of the universe influences this growth by affecting how quickly matter can collapse into structures. Observations indicate that the rate of expansion has changed over cosmic history, influenced by the balance between matter and a component known as dark energy. Dark energy is associated with the accelerated expansion observed in the universe today. Its nature remains uncertain, but its effects are measured through the behavior of distant galaxies and supernovae. Within this region, the question of expansion continues to shift away from the idea of an outer boundary. The cosmic web exists entirely within the universe. Its growth and arrangement do not suggest that the universe is pushing into an external medium. Instead, the web stretches and evolves as the distances between its parts change. The expansion is embedded in the relationships between regions, not in their movement into something beyond. The visual impression of the cosmic web can suggest a network suspended in space. But this impression can be misleading if it implies an external frame. The web is not hanging within a larger void outside the universe. It is the universe's own large-scale structure. Every filament, cluster, and void is part of the whole. Observers within any part of this structure would see similar patterns on large scales, shaped by the same processes. The calm view of this region emphasizes continuity. The ancient light provides the initial conditions. The expansion sets the scale. Gravity shapes the distribution. Dark matter forms the scaffolding. Dark energy influences the rate of growth and separation. Together, these elements create the cosmic web, a vast and intricate pattern that fills the observable universe. It is not bounded by an edge into which it expands. It is a manifestation of how matter and space evolve together. As attention moves further inward, the web gives way to more localized regions where the balance between gravity and expansion shifts. Clusters become distinct systems, and the influence of expansion becomes less dominant within them. Yet the memory of expansion remains in the separations between these systems. The cosmic web stands as a bridge between the uniform early universe and the more complex structures seen at smaller scales, all within a universe that expands without requiring an outside. Within the large cosmic web, the next inward region is the deep void. A cosmic void is a vast region where galaxies are much less common than in the surrounding filaments and clusters. It is not an absolute emptiness, and it is not an outside beyond the universe. It is a part of the universe where matter is thinly spread. The void belongs to the same expanding space as the brighter structures around it. Its quietness is important because it shows how expansion behaves where gravity has gathered less matter and where the large-scale stretching of distances remains more visible. A void forms from the same early variations that shape the rest of the cosmic web. In the young universe, some regions contain slightly more matter than average, while others contain slightly less. the denser regions pull matter toward themselves through gravity. The less dense regions lose matter over time as material flows away into the growing filaments and clusters. As this process continues, the underdense regions become larger and emptier in comparison with their surroundings. The void is therefore not carved out by a force pushing matter away into an exterior. It develops because gravity draws matter toward denser places inside the universe. The scale of a cosmic void can be immense. Some stretch across tens or even hundreds of millions of light years. Their sizes are measured through galaxy surveys that map where galaxies are and where they are scarce. A void may contain faint galaxies, thin gas, dark matter, and radiation, but it has far fewer bright galaxies than the denser parts of the web. Its emptiness is relative. It is an emptiness of low density, not an emptiness outside physical law. Space, time, light, gravity, and expansion are still present there. In this thin region, expansion is easier to picture as a change in distance between places that are not strongly bound. Galaxies at the edges of voids tend to belong to surrounding filaments and walls. The void itself grows in comparison with dense regions because matter continues to gather away from it, and because the expansion of the universe increases distances across large scales. This growth does not require the void to open into anything beyond the universe. It is growth within the pattern of space itself. The void expands as a region of a low density inside the cosmic web. The deep void also helps separate cosmic expansion from ordinary motion. A galaxy moving through nearby space has a local velocity. It can drift, fall toward a cluster, or orbit within a group. Cosmic expansion is different. Across the breadth of a void, the distance between separated regions can increase because the scale of space changes. The galaxies around a void can appear to recede from one another as the intervening space expands. No central point inside the void needs to push them outward. The process belongs to the geometry of the wider universe. Dark matter remains present in voids, though at lower density than in filaments and clusters. It does not shine, and it is detected through gravity. In dense places, dark matter gathers into halos that host galaxies and groups. In voids, the dark matter distribution is more diffuse, and fewer halos grow large enough to host bright galaxies. This difference helps explain why voids look empty in optical maps. The lack of visible galaxies does not mean the region lacks all substance. It means the conditions there produce fewer luminous structures. Gas also exists in and around voids, often thin and difficult to detect. Some of it may be warm or hot, spread across the spaces between galaxies. Some may be associated with faint galaxies that live inside voids. These galaxies can be small, isolated, and slowly evolving. They are useful to astronomers because their relative isolation can preserve information about how galaxies form when interactions are rare. Still, the void remains defined by what it lacks in comparison with the cosmic web around it. It is a quiet region of reduced crowding. The existence of voids does not contradict the large-scale uniformity of the universe. Uniformity applies only when enormous regions are averaged together. On smaller cosmic scales, the universe is highly uneven. Dense clusters and sparse voids can both exist within a universe that is statistically smooth across much larger volumes. This distinction is important. The universe is not smooth like a polished stone at every scale. It is smooth only when the pattern is viewed broadly enough that local structures blend into an average. The void also shows why the phrase empty space can mislead. Space is not nothing in the simple sense. Even where matter is sparse, space has measurable geometry. Light crosses it. Gravitational effects pass through it. Quantum fields, The underlying fields associated with particles and forces are present according to modern physics. The expansion of the universe is not the spreading of galaxies into a blank absence outside everything. It is the changing of distances within this physical setting, even in regions where very little ordinary matter is found. When observations map voids, they show no sign of an outer cosmic edge. A void may look like a dark gap in a galaxy map, but it is surrounded by structure and belongs to the same connected universe. Its darkness is not an opening into a beyond. It is part of the arrangement of matter. It has a history, a density, a shape, and a relation to the surrounding filaments. It can grow, merge with neighbouring underdense regions, and change as the universe evolves. All of this happens within the same cosmic geometry. The deep void is therefore a place where the answer to the expansion question becomes especially clear. Even in the emptiest known regions, expansion is not described as space pouring into a container. The void is already space. Its distances change with the universe's scale. Its low density allows expansion to shape it strongly, while gravity continues to organize matter around its edges. Nothing in the void suggests a surface where the universe meets an outside. It is an inner emptiness, a quiet low-density region within the whole. The calm image is one of sparse galaxies, faint matter, thin gas, and wide distances. The void deepens because matter has flowed toward denser regions, and because expanding space increases the separations that define it. It is not a hole in reality. It is not a window through the universe. It is a region of the universe where there is less matter, more distance, and a clearer view of the difference between ordinary emptiness and an outside that observations do not require. At the denser crossings of the cosmic web, the next inward region is the galaxy cluster. A galaxy cluster is a large bound system containing many galaxies, hot gas, dark matter, and the shared gravity that holds them together. It is different from the wide void because matter is concentrated there. It is different from the broad expansion because the cluster's own gravity dominates within its region. The universe still expands on larger scales, but inside a mature cluster, the galaxies and gas are not simply carried apart by that expansion. They belong to a common gravitational system. A cluster forms where matter gathers over long periods. In the early universe, slight density differences provide the starting points. Regions with more matter attract still more matter. Dark matter collects first into large halos, and ordinary matter falls into the same gravitational wells. Gas heats as it falls inward. Galaxies form, merge, and move within the growing system, over billions of years. These processes create clusters that can contain hundreds or even thousands of galaxies. The cluster becomes one of the largest kinds of structure held together by gravity. The space inside a galaxy cluster is not empty. It contains a hot, thin gas spread between the galaxies. This gas is called the intracluster medium, meaning the matter that lies among the cluster's galaxies. It reaches very high temperatures because gravity accelerates the gas as it falls inward, and collisions among gas particles convert motion into heat. The gas becomes hot enough to emit X-rays, a form of high-energy light. X-ray observations reveal the presence of this gas and help measure the cluster's mass and structure. The gas can contain more ordinary matter than the galaxies themselves. Dark matter makes up much of the cluster's mass. It does not shine, but it shapes the motion of galaxies and the distribution of hot gas. The evidence for dark matter in clusters comes from several lines of observation. Galaxies move too quickly to be held together by the gravity of visible matter alone. Hot gas also requires a deep gravitational well to remain bound. In addition, Clusters bend the light of more distant objects through gravitational lensing. Gravitational lensing is the bending of light by mass. The amount of bending shows that much more mass is present than the visible galaxies and gas can provide. Within the cluster, expansion gives way to binding. The galaxies are not fixed in place, but their motion is governed mainly by the cluster's gravity. They move through the cluster, sometimes passing near one another, sometimes interacting, and sometimes merging. Their paths can be complex, but they remain part of the same bound system. The expansion of the universe does not stretch the distances between galaxies inside a stable cluster in the same way it stretches distances between far, unbound regions. Local gravity has gathered the matter into a shared region that resists the general cosmic scaling. This does not create a conflict with universal expansion. Expansion is not a force that must pull every object apart at every scale. It is a feature of the large-scale geometry of the universe, where matter is sparse and regions are not bound. Distances grow with the cosmic scale. Where gravity has formed a stable system, the system's internal distances are governed by local dynamics. A cluster can remain bound while the distance between that cluster and other far clusters increases over time. The universe can expand and clusters can stay together. The boundary of a cluster is not a sharp wall. The density of matter gradually decreases outward. Galaxies near the outskirts may be falling in for the first time. Groups of galaxies can be accreted, meaning drawn into the cluster by gravity. Some regions around the cluster connect to filaments of the cosmic web, along which matter continues to flow. The cluster sits as a dense node in the wider structure. Its inward gravity gathers matter from its surroundings. While the larger universe continues its expansion across greater distances, collisions between galaxy clusters show this balance in dramatic but still natural form. When two clusters meet, their galaxies mostly pass through one another because the spaces between stars and galaxies are large. Their hot gas, however, collides and slows, producing shock waves and bright X-ray emission. Dark matter appears to pass through more easily, revealed by lensing maps that do not always align with the hot gas. Such events help confirm that clusters are complex systems made of several components. They also show that gravity and local motion dominate within these dense regions, not the smooth stretching seen across the largest cosmic scales. The galaxies inside clusters often differ from galaxies in less crowded environments. Many cluster galaxies are elliptical, meaning their stars are distributed in rounded or elongated shapes without the strong spiral arms seen in some isolated galaxies. Many have older stellar populations and less active star formation. The dense environment can strip gas from galaxies as they move through the hot intracluster medium. Without enough cold gas, new stars form more slowly. The cluster environment therefore shapes the life of its galaxies. The same gravity that binds the cluster also influences the material available for future star formation. The hot gas within clusters keeps a record of many processes. It contains elements heavier than hydrogen and helium, produced in stars and released by stellar winds and supernovae. These elements spread into the intracluster medium through the history of galaxy formation and interaction. The gas therefore carries evidence of both cosmic structure and stellar life. Its pressure, temperature, and distribution reveal how the cluster has grown and how energy moves through the system. Yet all of this remains within a bound region of the universe, not at an outer boundary. A galaxy cluster shows clearly that expansion does not mean everything expands in the same way. The cluster's internal scale is held by gravity. Its galaxies move in a shared gravitational field. Its hot gas remains trapped by the cluster's mass. Its dark matter halo shapes the whole system. At the same time, the cluster participates in the wider universe. Light from other clusters is red-shifted by expansion. The distances between unbound clusters increase across cosmic time. The cluster is a stable island in an expanding sea of large-scale distance, though the sea is not outside the universe. It is only the wider geometry around the bound system. This inward region therefore gives a quieter and more precise answer to the central question. Space is not seen expanding into a surrounding emptiness. An expansion is not a simple pulling apart of every object. It is a large-scale increase of separation, where gravity has not bound regions together. A galaxy cluster remains together because its gravity is strong enough to shape its own domain. Beyond the cluster's bound region, the wider cosmic scale continues to change. Within the cluster, matter gathers, gas glows, galaxies move, and gravity holds the structure close. Within the bound richness of clusters and groups, the next inward region is the individual galaxy. A galaxy is a system of stars, gas, dust, dark matter, and gravity. It may be shaped as a spiral, an ellipse, an irregular cloud of stars, or a form between these types. It can contain millions, billions, or even trillions of stars, depending on its size. A galaxy is large by human measure, but it is small compared with the distances between galaxies in the wider universe. This difference in scale is central to understanding why galaxies themselves do not expand in any meaningful way with cosmic expansion. A galaxy forms where matter has collapsed under gravity into a bound structure. Dark matter gathers into a halo, a broad invisible region whose gravity helps hold ordinary matter. Gas falls into this halo, cools, and becomes dense enough in some places to form stars. Stars gather into patterns shaped by gravity, rotation, and the history of mergers with smaller systems. In a spiral galaxy, much of the gas and many young stars lie in a flattened disk. While older stars may fill a central bulge and a wider halo, in an elliptical galaxy, stars move in more varied orbits, and the system often contains less cold gas for new star formation. Inside a galaxy, gravity dominates over the large-scale expansion of the universe. Stars do not drift apart because space between them is expanding in the same way that distances between distant galaxy clusters expand. Their motions are governed by the galaxy's gravitational field. A star orbits within the combined gravity of the stars, gas, and dark matter around it. Gas clouds move, collide, cool, and form stars. Dust absorbs and scatters light. The galaxy behaves as a bound system, and its internal structure is maintained by local gravity rather than carried outward by cosmic stretching. This does not mean the universe stops expanding inside the region where a galaxy exists. It means that the mathematical description of smooth cosmic expansion is not the best description of the galaxy's internal behavior. The large-scale expansion applies to the average universe across enormous distances, where matter is spread broadly and not strongly bound into one system. A galaxy is a dense departure from that average. Its gravity has separated it from the general flow. The distances between its stars are not increasing with the cosmic scale factor, because the stars are part of a stable gravitational structure. The difference can be understood by comparing a galaxy with the wider space between unbound galaxies. Between two distant galaxies that are not part of the same group or cluster, the space separating them can grow as the universe expands. Inside one galaxy, stars are already tied into orbits. Their separations change because of local motion, close encounters, stellar evolution, and gravitational disturbances, not because of the smooth expansion measured across the universe. Cosmic expansion is real, But it is not the force that overcomes every local bond. The dark matter halo of a galaxy strengthens this binding. Although dark matter does not shine, its gravity strongly affects the galaxy's rotation and stability. In many spiral galaxies, stars and gas in the outer disk move faster than expected from visible matter alone. This pattern is one of the main reasons astronomers infer the presence of dark matter halos. The halo extends beyond the bright visible disk, surrounding the galaxy with an unseen gravitational field. This field helps hold the system together and further separates its internal dynamics from the broad expansion between distant structures. Gas within a galaxy follows local conditions. It can be cold and dense in molecular clouds, where new stars form. It can be warm or hot in regions shaped by stellar radiation, winds, and supernova explosions. A supernova is the explosive death or disruption of a star that releases energy and heavy elements into surrounding space. These processes stir and enrich the gas, but they do not show the galaxy expanding with the universe. They are internal events, driven by stars and gravity. The galaxy changes through its own history while the larger universe expands around and between bound systems. Dust also belongs to this inner galactic region. It consists of tiny solid grains made from elements formed in stars. Dust can darken visible light and glow in infrared light after being warmed by stars. It marks regions where gas is dense, and it helps reveal the cycle of star birth and stellar death. Its motion is shaped by gravity, radiation, magnetic fields, and gas flow. Like stars and gas, dust is part of the bound system. It does not provide evidence of cosmic expansion inside the galaxy. It records local physical processes. Galaxies can grow by merging with other galaxies. When two galaxies pass close enough, gravity can distort their shapes, stretch tidal tails, trigger bursts of star formation, and eventually combine them into a larger system. These mergers are not caused by cosmic expansion. They occur because local gravity pulls nearby systems together when they are bound or moving within the same gravitational environment. In fact, such mergers show the opposite of simple universal separation at local scales. Nearby galaxies can approach each other despite the expansion of the universe on larger scales. The light from a galaxy carries two kinds of motion information. One is the galaxy's local motion, caused by gravity within its neighborhood. The other is the cosmological redshift, caused by the expansion of space during the light's long travel through the universe. For nearby galaxies, local motion can be large enough to dominate the observed redshift or even produce a blue shift, meaning light is shifted towards shorter wavelengths. For very distant galaxies, cosmic expansion usually dominates. The balance between these effects depends on distance and environment. This is why individual galaxies must be understood both as local systems and as markers in the larger expanding universe. The galaxy is therefore an inner region where the expansion question becomes more precise. Space is not expanding into an outside, and cosmic expansion is not making every smaller structure swell. A galaxy remains itself because gravity organizes its stars, gas, dust, and dark matter into a bound whole. Its size can change through mergers, star formation, gas loss, and interaction. But these are local histories. The general expansion appears most clearly between galaxies that are far apart and not gravitationally bound. Within a galaxy, the universe is not a smooth average. It is textured with spiral arms, star clusters, nebulae, dark dust lanes, and quiet halos of old stars. The galaxy carries evidence of cosmic history, but it does not behave as a miniature version of the expanding universe. It is a settled island of gravity within the larger pattern. The distances inside it are shaped by orbital motion and binding, while the distances beyond its local reach can increase with cosmic time. In this inward region, expansion is still real, but it becomes a background property of the universe rather than the ruler of every local distance. Within the scale of individual galaxies, the next inward region is the local cosmic neighborhood around the Milky Way. This region includes the Milky Way itself, nearby smaller galaxies, the Andromeda Galaxy, the Triangulum Galaxy, and many faint dwarf galaxies held together in a shared gravitational environment. It is called the local group. The name is simple, but the region is important because it shows how cosmic expansion and local gravity can produce different motions at the same time. The wider universe expands, yet nearby galaxies can still approach, orbit, and bind together. The Milky Way is a spiral galaxy with a broad disk of stars, gas, and dust, surrounded by a faint stellar halo and a larger dark matter halo. Near it are smaller companion galaxies, including the Large Magellanic Cloud and the Small Magellanic Cloud. These companions move under the Milky Way's gravity while also carrying their own stars and gas. Farther across the local group lies Andromeda, another large spiral galaxy. Its light is shifted slightly toward shorter wavelengths, which indicates that it is moving toward the Milky Way rather than away from it. This motion is local. It does not contradict the expansion of the universe. It shows that gravity dominates inside this bound neighborhood. The local group is not expanding in the same way that distant unbound regions expand. Its members are tied together by mutual gravity. The dark matter halos of the Milky Way and Andromeda hold much of the mass in the region. Smaller galaxies move within this shared gravitational field. Some dwarf galaxies orbit larger galaxies. Others may be falling inward or following long paths shaped by past interactions. The distances among these nearby galaxies change because of local motion, not because they are simply being carried apart by the overall growth of cosmic distance. This local region helps separate two meanings that can otherwise blend together. Recession caused by cosmic expansion is the large-scale increase in distance between unbound regions of the universe. Peculiar motion is the motion of an object relative to that smooth expansion, caused by local gravity. The word peculiar here does not mean strange. It means individual or local. A galaxy can have a cosmological redshift from expansion and also a peculiar motion from gravity. Nearby galaxies often have peculiar motions large enough to dominate what is observed. The local group is close enough and bound enough that these local motions matter most. Around the local group, there are other nearby structures. Some galaxies belong to nearby groups. Farther away, larger collections such as the Virgo cluster influence motions across the region. The Milky Way and its neighbours are not isolated in a perfect emptiness. They sit within a wider flow of matter shaped by the cosmic web. Gravity from nearby groups and clusters affects how galaxies move. Still, the local group itself remains a bound region. Its internal motions cannot be understood by applying the smooth expansion of the universe alone. This distinction is visible in the way distances are measured. For far galaxies, redshift is often used as a guide to distance because the expansion of space creates a broad relation between the two. For galaxies in the local group, redshift is not a reliable distance ruler by itself. A nearby galaxy may move toward the Milky Way, sideways across the sky, or along a complex orbit. Its light may show blue shift or only a small redshift. Astronomers therefore use other methods, such as variable stars and stellar brightness patterns, to determine distances in the local neighborhood. These methods rely on the known behavior of stars rather than the expansion of space. The local group also shows that the universe is not expanding from a center near the Milky Way. If expansion were a simple explosion from one location, nearby objects might be expected to share a clear outward motion from that point. Instead, the local pattern is governed by gravity. Andromeda approaches. Dwarf galaxies orbit. Streams of stars are torn from smaller systems by tidal forces. Tidal forces are differences in gravity from one side of an object to another, stretching or disturbing it. These local effects are natural in a gravitational group and do not require any outward push from a cosmic center. The Milky Way's own motion adds another layer. The Sun orbits the center of the Milky Way. The Milky Way moves within the local group. The local group moves relative to the cosmic microwave background. These motions are measured by observing the direction in which the background radiation appears slightly warmer and the opposite direction in which it appears slightly cooler. This pattern reflects motion through the ancient radiation field. It is a local motion of the observing region, not evidence that the universe has a central rest point. The background provides a useful reference frame for cosmic measurements, but it is not an outer container. The local neighborhood also contains quiet signs of past interaction. Some dwarf galaxies show distorted shapes. Some streams of stars stretch through the Milky Way's halo, remnants of smaller systems pulled apart by gravity. Gas clouds move around galaxies and between them. These structures reveal that nearby space is active in its own slow way. It is shaped by accretion, orbit, stripping, and merger. Accretion means the gradual gathering of matter into a larger system. None of these local processes depend on expansion into an outside. They are internal movements within a bound region of the universe. At the scale of the local group, cosmic expansion becomes a background condition that is overcome by local binding. The universe as a whole can expand while this neighborhood remains gravitationally connected. The distance between the Milky Way and a far unbound galaxy can grow because space expands between them. The distance between the Milky Way and Andromeda can shrink because their mutual gravity controls their motion. Both statements are part of the same scientific picture. Expansion applies most clearly across great unbound distances. Gravity controls smaller bound systems. This region therefore gives a grounded answer to the question of what expansion means nearby. It does not mean that every galaxy moves away from every other galaxy. It does not mean that space stretches all local distances in a way that breaks apart bound structures. It means that, when the universe is averaged over very large scales, distances between unbound regions increase. In the local neighborhood, the pattern is different because gravity has gathered galaxies into a shared domain. The local group is an inward step from the individual galaxy toward the familiar cosmic home of the Milky Way. It contains motion, but not the smooth recession seen across the far universe. It contains distance, but not the kind of distance ruled mainly by expansion. It contains ancient light and local gravity together. The calm lesson is that expansion is not a universal wind blowing every object outward into a surrounding void. It is a large-scale change in cosmic distance. While nearby bound regions follow their own gravitational paths. Within the local neighborhood of the Milky Way, the next inward region is the solar system. This region is shaped by the gravity of the Sun, the motion of planets, the paths of moons, the smaller bodies of rock and ice, and the thin flow of particles and radiation moving outward from the Sun. It is a local system, deeply bound compared with the broad distances between galaxies. The expansion of the universe exists as part of the large-scale cosmic description, but does not stretch the solar system in any measurable everyday way. The planets do not drift away from the Sun because space itself is expanding between them. Their motions are governed by local gravity. The Sun contains almost all the mass of the solar system. Its gravity holds the planets in orbit: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune follow paths that are stable over human timescales, though their orbits slowly change under mutual gravitational influence. Moons orbit planets. Asteroids occupy many regions, especially between Mars and Jupiter. Comets travel on long paths that can carry them far from the Sun and then back inward. Every object in this system responds to the gravity of nearby masses far more strongly than to the general expansion measured across intergalactic distances. This difference is a matter of scale and binding. Cosmic expansion becomes clear when astronomers measure the light from very distant galaxies that are not gravitationally bound to the Milky Way. The distances are enormous, and the systems are separated by expanding space. Inside the solar system, the distances are small by cosmic standards, and the gravitational field of the Sun dominates. Earth remains in orbit because its forward motion and the Sun's inward pull form a stable path. Cosmic expansion does not act like a hidden force that gradually loosens this bond. The local solution of gravity is not the same as the smooth average expansion of the universe. The solar system can be described with great precision using gravity, motion, and time. Spacecraft navigation depends on this precision. Paths to the Moon, Mars, Jupiter, Saturn, and other bodies are calculated using the gravitational fields of the Sun, planets, and sometimes moons. These calculations do not need to include a stretching of space from cosmic expansion in order to explain ordinary planetary motion. Any effect of the universe's expansion at this scale is far too small compared with local gravity, and is not part of the practical dynamics that guide planets and spacecraft. This does not mean the solar system is sealed away from the universe. It is immersed in the galaxy. It moves around the center of the Milky Way. It passes through interstellar gas and dust at very low density. It receives cosmic rays, which are high-energy particles from beyond the solar system. It is crossed by light from distant stars and galaxies, including light stretched by cosmic expansion. Yet these influences do not make the solar system expand with the cosmos. They show that the solar system is local and connected to larger surroundings, while still governed internally by its own gravitational balance. The Sun also creates a region called the heliosphere. The heliosphere is the broad bubble influenced by the solar wind, a stream of charged particles flowing outward from the Sun. This bubble reaches far beyond the planets and interacts with the thin material between stars. It is not a boundary of the solar system in the same way a wall is a boundary of a room, but it marks where the Sun's particle flow gives way to the interstellar environment, even here. Near the outer reach of solar influence, the structure is local. It is shaped by the Sun, the solar wind, magnetic fields, and the surrounding interstellar medium. It is not shaped by the universe expanding into an outer space. Planetary orbits reveal the quiet strength of local binding. Earth travels around the Sun once each year. The Moon travels around Earth in a shorter cycle. Jupiter's gravity shapes the asteroid belt and influences many smaller bodies. Neptune helps shape the distant Kuiper belt, a region of icy bodies beyond its orbit. Farther out, some comets may come from a distant reservoir of icy objects known as the Oort cloud, whose full structure remains difficult to observe directly. These layers are wide, but they remain part of a local gravitational system. Their distances do not increase simply because the universe expands. The objects of the solar system are also held together internally by forces stronger than cosmic expansion at their scale. A planet is bound by its own gravity. A rock is held together by electromagnetic forces between atoms and molecules. Ice, dust, and metal grains have local structure. These forces are not overcome by the smooth expansion seen between distant galaxies. The universe expands in its large-scale geometry, but stones do not swell. Oceans do not widen from cosmic expansion, and planetary surfaces do not stretch apart because of it. Local forces define local sizes. This inward region helps correct a common misunderstanding. When it is said that space expands, this statement applies to the large-scale universe after matter is averaged over immense distances. It does not mean every empty gap grows equally in every setting. The empty space between Earth and Mars is not treated like the empty space between remote galaxy clusters. The planets are part of one bound system. Their distances vary because of elliptical orbits, gravitational perturbations, and long-term orbital changes, not because the solar system follows the general cosmic expansion. The same idea applies to the distance between Earth and the Moon. The Moon is slowly moving away from Earth, but this is caused mainly by tidal interactions. Earth's rotation and the Moon's orbit exchange energy and angular momentum through tides. The effect is local and measurable. It is not the expansion of the universe. This example shows why careful explanations matter. A distance can increase for many reasons. Not every increasing distance is cosmic expansion. The cause must be identified through the physics of the system. The solar system therefore stands as a calm inner domain where cosmic expansion becomes almost silent. The same universe that stretches the wavelengths of distant galaxy light also contains stable planetary orbits. The same cosmic history that produces redshift and ancient microwave radiation also allows a star and its planets to remain bound for billions of years. There is no conflict because the laws act across different scales and conditions. Expansion describes the broad geometry. Gravity and other local forces hold smaller systems together. In this region, the question of what space expands into becomes less like a distant puzzle and more like a matter of choosing the correct scale. The solar system does not expand into anything. It moves within the Milky Way, held by the Sun and shaped by nearby gravity. The universe outside the local bound system can show expanding distances, but the planets do not need an outside container to keep their paths. They follow the curved motion set by gravity. The solar system is a small, stable realm inside a much larger expanding universe, and its stillness at this scale helps reveal that expansion is not a universal stretching of all things, but a large-scale change in distances where local binding does not rule. Within the stable scale of the solar system, the next inward region is the place of measurement, where observers on and near Earth turn expansion into evidence. Earthbound measures do not touch the expansion of space directly like a hand touching a surface. They infer it through light, distance, time, and comparison. A telescope collects photons from stars, galaxies, supernovae, and ancient radiation. Instruments separate that light into its wavelengths. Astronomers compare the received light with known patterns produced by atoms and molecules. From these comparisons, they measure redshift, distance, motion, and the history of cosmic expansion. The first important measure is redshift. Atoms emit and absorb light at specific wavelengths because their electrons change energy states in fixed ways. These patterns act like fingerprints. Hydrogen, helium, oxygen, calcium, and many other elements leave recognizable lines in a spectrum. A spectrum is light spread out by wavelength. When the same pattern is seen in a distant galaxy, but shifted toward longer wavelengths, the shift can be measured. For distant galaxies beyond the local gravitational neighborhood, this stretching is mainly caused by the expansion of space during the light's travel. The larger the redshift, the more the light has been stretched. Redshift alone is not enough. To understand expansion, astronomers also need distance. Distance in astronomy is built through several linked methods, often called a distance ladder. The first steps use nearby objects whose positions can be measured as Earth moves around the Sun. This method is called parallax, the apparent shift of a nearby object against more distant backgrounds when viewed from different positions. Parallax gives direct distances to nearby stars. These distances help calibrate other methods, including variable stars whose brightness changes in known ways. Some of these stars reveal their true brightness through their rhythm, allowing observers to compare true brightness with apparent brightness and estimate distance. For farther galaxies, other markers are used. Certain supernovae are especially useful because their brightness behavior can be calibrated. A supernova is a powerful stellar explosion or disruption, and some types reach a predictable intrinsic brightness when corrected through careful observations. Intrinsic brightness means how bright the object truly is, rather than how bright it appears from Earth. If the true brightness is known, the distance can be estimated from how faint the object appears. These distant markers show that the expansion of the universe has changed over time. Observations of such supernovae provide evidence that cosmic expansion is accelerating in the present era. Galaxy surveys add another layer. By measuring redshifts for large numbers of galaxies and estimating their distances, astronomers map the expanding universe statistically. They do not rely on one galaxy alone. They look for patterns across many objects. The relation between redshift and distance becomes clearer when many measurements are combined. Local motions can disturb individual cases, but large samples reveal the broad flow of expansion. The result is a universe in which distant unbound galaxies recede in a pattern tied to the growth of space. Another measure comes from baryon acoustic oscillations. Baryons are ordinary matter particles such as protons and neutrons. In the early universe, waves travelled through the hot mixture of matter and radiation. These waves left a preferred scale in the later distribution of galaxies. The phrase baryon acoustic oscillation refers to this ancient pattern, preserved as a slight excess of galaxy pairs separated by a characteristic distance. By measuring this scale at different redshifts, astronomers trace how cosmic distances have changed through time. It is a ruler built into the large-scale structure of the universe. The cosmic microwave background provides another ruler. Its tiny temperature variations contain patterns that depend on the contents, geometry, and expansion history of the universe. By comparing observed patterns with physical models, scientists estimate the age of the universe, the amounts of ordinary matter and dark matter, and the broad behavior of expansion. These estimates are not made from a single point of light. They arise from a detailed map of the ancient radiation field across the whole sky. The background acts as a record of early conditions and a test of how the universe grows from that state. Measurement also requires correction for local effects. Earth rotates. Earth orbits the Sun. The Sun orbits within the Milky Way. The Milky Way moves within the local group. The local group moves relative to the cosmic microwave background. These motions can shift observed light slightly. Dust can dim and redden light. Gravitational lensing can magnify or distort distant sources. Instruments have limits and uncertainties. Astronomers account for these effects as carefully as possible. The goal is to separate local motion, intervening matter, and measurement limits from the signal of cosmic expansion. Earthbound measures are therefore patient and indirect. They build confidence through agreement among different methods: redshift, supernova distances, galaxy clustering, gravitational lensing, and the cosmic microwave background all contribute to the same broad picture. The universe expands. Its expansion rate has changed with time. Matter slows expansion through gravity, while the observed late-time acceleration is associated with dark energy. The nature of dark energy remains uncertain, but its effects are included in the best current models because multiple observations require something like it to explain the measured history. In this region, the question of what space expands into becomes an issue of what is actually measured. No instrument observes a border of the universe moving into an outside. No telescope sees a surface pushing against a larger emptiness. The measurements show stretched light, changing distance scales, ancient radiation, and large-scale structure. They show that the relationships between far regions change over cosmic time. The evidence is internal. It comes from signals travelling within the universe and arriving at instruments within the universe. A ruler on Earth does not expand with the universe, because it is held together by electromagnetic forces among atoms. A laboratory does not stretch with the cosmic scale. A telescope mirror keeps its shape through material forces. These stable local systems allow observers to measure distant expansion. If every local ruler expanded in exactly the same way as cosmic distances, the effect would be impossible to detect. The fact that local bound systems remain stable, while distant unbound regions show redshift, makes expansion measurable from within. The earthbound observer therefore occupies a quiet middle position. The instruments are local, fixed by matter and forces. The light is cosmic, carrying records from immense distances and ancient times. Between the local instrument and the distant source lies expanding space, revealed through stretched wavelengths and consistent patterns. The observer does not stand outside the universe to see it grow. The observer remains inside it, using light as a messenger and physics as a way to compare one region with another. This inner region of measurement gives the expansion question a practical answer. The evidence for expansion is not a picture of the universe from outside. It is a set of relationships measured from within. The universe is known by the light it sends, the patterns it preserves, and the distances inferred through careful methods. These measurements show changing scale, not motion into a container. They reveal a cosmos whose growth is read in wavelengths, brightness, timing, and structure, all from a small planet held quietly in orbit around an ordinary star. Within the region of measurement, the next inward layer is mathematical space, where observations are translated into geometry. In this layer, expansion is not treated as a substance spreading outward. It is described as a change in the distances between far apart points when the universe is averaged on the largest scales. The main framework is general relativity, the theory in which gravity is understood as the geometry of space and time. Space and time are not a stage placed inside another stage. They are part of the structure being described. When cosmology says space expands, it means that this structure changes with time in a measurable way. The word geometry usually brings to mind shapes, lines, angles, and distances. In cosmology, geometry has a broader meaning. It includes how distances are measured, how light travels, and how matter and energy affect the path through space and time. A galaxy does not need to know this mathematics to move, and light does not need to choose its path. The equations describe what happens. They connect the contents of the universe with the way the universe changes. Matter, radiation, dark matter, and dark energy all contribute to the large-scale behavior of expansion. A central idea in this mathematical layer is the metric. A metric is a rule for measuring distances and intervals. In ordinary life, distance can be measured with a ruler across a floor. In the universe, the metric describes distances across space and time, including how those distances change. The cosmological metric used for a smooth expanding universe has a scale factor. This scale factor tells how the separation between far, unbound regions changes as time passes. It does not describe galaxies moving through a fixed emptiness. It describes the growth of the measured spacing in the large-scale geometry. This is why the question of an outside becomes less necessary in mathematical space. A surface, such as the surface of a sphere, can have a complete geometry that is defined within itself. A small creature moving on that surface could measure distances and angles without needing access to a higher surrounding space. This comparison is limited because the real universe is not simply a two-dimensional surface, but it helps show that geometry does not always require an external container. A space can be finite or curved in its own terms without having an edge that belongs to its own geometry. Cosmology works with the geometry that can be measured from within the universe. In the standard expanding models, every large-scale distance can grow according to the scale factor. The coordinates used to label far regions can remain fixed, while the physical distances between them increase. These fixed labels are called comoving coordinates. Comoving means moving along with the general expansion. A galaxy at rest in these coordinates is not stationary in the sense of being fixed inside a larger room. It is simply following the average cosmic flow. The physical distance to another such galaxy grows because the scale factor grows. This language allows expansion to be described without placing the universe inside an outside space. The mathematics also separates local curvature from global expansion. Local curvature appears near masses, such as stars, galaxies, and clusters, where gravity bends paths and shapes motion. Global expansion describes the average change of the universe across vast scales. These are part of the same theory, but they apply differently depending on scale. Near Earth, the geometry is dominated by the Sun and the planets for most practical purposes, across intergalactic distances. The average expansion becomes the central feature. The same framework can include both a stable orbit and a growing cosmic distance. The question of what space expands into often comes from imagining space as if it were a material sheet. But mathematical space is not a sheet with an edge pressed into another region. It is a set of relationships among events, distances, and times. An event means something located at a place and time, such as the emission of a photon from a galaxy, or the arrival of that photon at a telescope. The geometry tells how such events are connected. When expansion is described mathematically, the changing relationship between events is enough. No external room is required by the equations. The mathematical models do not claim that every detail of the universe is smooth. Galaxies, stars, and planets are uneven structures. To describe the universe as a whole, cosmology averages over these details on very large scales. This produces a smooth model that can be compared with observations of redshift, background radiation, and galaxy patterns. The model is an approximation, but a powerful one. It captures the broad behavior of the universe while smaller structures are treated as local variations within it. This is why expansion belongs to the large-scale description rather than to every small region equally. In this layer, time also has a special role. The universe is not merely a sequence of still spaces, it is a changing space-time structure. The scale factor depends on cosmic time, a time coordinate that follows observers moving with the average expansion. This does not mean every observer experiences time in exactly the same practical way. Because local gravity and motion can affect time measurements, it means that, for the large-scale smooth model, there is a useful shared time used to describe the history of expansion. With this time, the universe can be described as hotter and denser in the past, cooler and more spread out at present. The contents of the universe determine how the scale factor changes. Ordinary matter and dark matter attract through gravity and tend to slow expansion. Radiation also contributes, especially in the early universe. Dark energy is associated with the observed accelerated expansion at late times. The exact physical nature of dark energy remains uncertain. In the standard model, it behaves like a nearly constant energy density of space. But observations continue to test whether this description is complete. The mathematical framework allows these possibilities to be stated carefully, using measurements rather than speculation. Mathematical space also makes clear that expansion has no need to begin from a point inside space. In the standard cosmological description, earlier times correspond to a smaller scale factor, meaning that distances between far regions were smaller. This does not mean all matter exploded from a central point into an empty background. It means the whole observed region was once hotter, denser, and smaller in scale. Every large region participates in that earlier dense state. The mathematics describes a change of scale everywhere in the model, not a blast outward from one location. This inward layer is quiet because it removes the need for many images. The universe is not a cloud, a bubble, or a sphere expanding into a surrounding chamber in the way ordinary objects do. Those pictures can help briefly, but they can also mislead. The mathematical description is more restrained. It says that the measured distances between far, unbound regions change with time. It says light is stretched as it travels through this changing geometry. It says the expansion rate depends on the contents of the universe. It does not say that an exterior space receives the expanding cosmos. Within mathematical space, the answer becomes plain in form, though not simple in feeling. Expansion is a property of the universe's geometry. It is described from within by rulers that remain locally bound, clocks that measure time, and light that carries redshift across distance. It does not require the universe to be embedded in a larger emptiness. The known equations work without such an outside. What is measured is not an outward surface, but a changing scale, written into the pairs of light and the distances between the great unbound regions of the cosmos. Within mathematical space, the next inward idea is the absence of a cosmic center. This region is not a place in the universe, but a way of understanding the pattern of expansion from inside it. In ordinary experience, expansion often has a center. A firework spreads from one point. A drop of dye spreads from one location in water. A cloud of gas moves away from a source. These familiar images make it natural to search for a central place from which all galaxies move outward. Observations and cosmological models do not support such a center within the universe. The expansion appears as a large-scale increase of distance between far regions, seen from every suitable location in the same general way. The absence of a center follows from the large-scale uniformity of the observed universe. When averaged over enormous distances, the universe appears nearly the same in all directions. Galaxies gather into clusters, filaments, and voids. But the broad statistical pattern has no observed special point. The cosmic microwave background also arrives from every direction, with almost the same temperature after local motion is accounted for. These observations support the idea that no location in the observed universe is the central point of expansion. Earth is central only to Earth's observable region. because light arrives at Earth from all directions. That is an observational centre, not a physical centre of all space. Every observer has an observable universe centred on themselves. This sounds special only because reception of light always places the receiver at the middle of the received view. A galaxy far away would see its own horizon, its own farthest ancient light, and its own surrounding sphere of arriving signals. It would not see Earth as the centre. It would see itself at the centre of its own observations. The same would be true for many locations, provided they are not inside extreme local environments that distort the view strongly. This symmetry is one of the reasons the idea of a single central point is not useful in modern cosmology. The redshift of distant galaxies can also be misunderstood as evidence of a centre. From the Milky Way, most far unbound galaxies appear to recede. This can feel as if the Milky Way is near the middle of an outward flow, but an observer in one of those far galaxies would see a similar broad pattern. The Milky Way's light would be redshifted from that observer's point of view, and many other distant galaxies would also appear to recede. The pattern is not centered on the Milky Way. It is a property of expanding distances. In an expanding geometry, every widely separated region can see other far regions moving away in the average pattern. This is different from an explosion in ordinary space. In an explosion, fragments move through a pre-existing environment from a source location. If observers rode with different fragments, they could in principle trace the motions backward to a central site. The density of fragments and their speeds might reveal where the event began. Cosmic expansion is not described this way. The earlier universe is not a point inside today's space. It is an earlier state in which the scale factor was smaller everywhere in the observed region. Looking back in time means finding that distances between far regions were smaller, not that galaxies all occupied one location in the surrounding void. The no-center idea can be expressed through the scale factor. When the scale factor grows, the physical distances between far co-moving regions grow. Each region can keep its co-moving position, while the distances between all such regions increase. There is no coordinate point that must remain fixed as the central source. Coordinates are labels, not physical markers of a cosmic middle. Different coordinate choices can describe the same expanding universe, and none of them needs to place a real center inside space. The expansion belongs to the relationships among all large-scale regions. This inward idea also helps answer why distant galaxies can recede in every direction. If expansion were motion away from a center, then galaxies on one side of the sky might show a different pattern from galaxies on the opposite side, depending on where the observer sits relative to the center. Instead, after local motions are removed, observations show a high degree of a large-scale isotropy. Isotropy means the universe looks broadly the same in every direction. This does not prove that the entire universe beyond observation is perfectly uniform, but it strongly supports models in which the observed expansion has no central point. There are small departures from perfect symmetry, and they matter scientifically. The Milky Way moves relative to the cosmic microwave background. Nearby galaxies have their own motions. Dense clusters pull matter. Voids expand relative to their surroundings. These effects create local patterns, but they do not define a center of the universe. They are smaller scale variations inside the larger expansion. A local flow toward a cluster is not the same as a cosmic origin point. A slight temperature pattern caused by motion through the microwave background is not a sign that the background has a central source. The absence of a center does not mean the universe has no structure. It has abundant structure. The cosmic web is rich with filaments, clusters, and voids. Galaxies have centers. Clusters have dense cores. The Milky Way has a central region containing a supermassive black hole. The solar system has the Sun as its dominant gravitational center. Centered systems exist at local scales because gravity gathers matter into bound forms. The statement that cosmic expansion has no center applies to the universe on its largest measured scales, not to every structure within it. This distinction keeps the explanation calm and precise. A galaxy can have a center while the universe does not need one. A cluster can have a dense middle, while cosmic expansion has no central source. A planet can orbit a star while distant galaxies recede because of expanding space. Local centers arise wherever matter is bound and organized. The large-scale expansion is different. It is a change in distances across the whole average geometry. At this level, the question of what space expands into becomes closely tied to the question of where expansion begins. If there is no center inside the universe, then expansion is not a spreading from a point into outer room. It is not a wave moving outward through pre-existing emptiness. It is the growth of scale in all large regions of the model at once. This growth is measured through redshift, ancient radiation, and large-scale structure. It does not identify a middle location, and it does not reveal an outer surface. The no-center picture is sometimes difficult because human experience is built from objects in surroundings. Every growing object seems to have an inside, an outside, and often a center. Cosmology asks for a different category. The universe is not treated as one object placed inside a larger room. It is the whole spatial setting described by the model. Within that setting, distances can change without requiring a central point. Observers inside the setting measure the change by comparing light and distance, not by watching the universe from beyond itself. The calm result is a universe where every far region participates in expansion, without any region being the source of it. Earth is not the center. The Milky Way is not the center. No observed galaxy holds that role. The expansion has no known center because it is not an outward motion from a point. It is a large-scale change in the relations between places. The farther inward the explanation moves, the less the question resembles a search for a location, and the more it becomes a description of geometry. Space expands not from somewhere into somewhere else, but through the changing distances that every suitable observer can measure from within. Within the idea that expansion has no center, the next inward region is the possible global shape of the universe. This region concerns the whole arrangement of space beyond the part that can be directly observed. It is one of the most careful areas of cosmology. Because observations reach only a finite horizon, the visible universe can be measured in detail, but the entire universe may extend far beyond it. Scientific statements about the total shape must therefore separate what is strongly indicated from what remains uncertain. Observations show that the observable universe is very close to spatially flat on large scales. They do not yet determine whether the whole universe is finite or infinite. Spatial flatness is a statement about geometry. In a flat space, on large scales and ignoring local distortions from matter, the familiar rules of distance behave much like ordinary Euclidean geometry. Parallel lines remain parallel, and the angles of large triangles add in the familiar way. Curved space can behave differently. Positive curvature can be loosely compared with the surface of a sphere, where paths that begin parallel can eventually meet. Negative curvature can be loosely compared with a saddle-like surface, where paths spread apart more strongly. These comparisons are only aids, because the universe has 3 spatial dimensions rather than the 2 dimensions of a surface. Measurements of the cosmic microwave background are central to this question. The tiny temperature patterns in that ancient light have a characteristic angular scale. By comparing the observed scale with physical models, scientists infer the large-scale curvature of space. Current observations indicate that space is very close to flat within the observable region. Close to flat does not necessarily mean exactly flat. It means any curvature, if present, is small enough that it is difficult to detect across the visible universe. The whole universe could be exactly flat, or it could have curvature so gentle that the observable region shows only a small part of it. A flat universe can be infinite, extending without end in every direction. It can also be finite in some mathematical forms if space is connected in a more complex way. A simple example is a flat space that wraps around on itself, though no such wrapping has been detected in the observed sky. A positively curved universe can be finite without having an edge. Somewhat like the surface of a sphere is finite in area, but has no boundary on the surface itself. A negatively curved universe is often infinite in simple models, though mathematics allows more varied possibilities. The important point is that finite does not have to mean edged. A finite space can be complete within itself. This distinction matters for the question of what space expands into. If the whole universe were finite and positively curved, it would not need an outer wall. The distances within it could grow, while the space remains without an edge. If the whole universe were infinite, it would also not need an outside, because an infinite space can expand by increasing the distance scale between points while remaining infinite. Infinity does not become larger in the ordinary sense of gaining an exterior border. Instead, the scale of separation changes. In both cases, expansion does not require a surrounding container. The observable universe cannot settle this fully because the horizon limits direct access. It is possible for the visible region to look almost flat even if the entire universe has slight curvature on far larger scales. This is similar to how a small patch of Earth can look flat even though Earth is curved. The comparison is useful only for the idea of limited view. The universe is not known to be a surface like Earth. The point is that observation over a limited region may not reveal the total shape. Cosmology, therefore, treats global shape with caution. The topology of the universe is another part of this region. Topology means the way space is connected. Curvature describes local or large-scale bending, while topology describes whether space loops back on itself or has a repeating connection. A universe could have no edge and still have paths that, in principle, return to a starting region after travelling far enough in one direction. Astronomers have searched for signs of such connections, such as repeating patterns in the cosmic microwave background or duplicate images of distant structures. No confirmed evidence has shown that the observable universe wraps around in this way. The lack of detected wrapping does not prove that space has no such global connection. It may mean that any repeating scale is larger than the observable universe, or that the universe does not have that topology. The evidence remains limited by the horizon and by the precision of observations. Scientific restraint is necessary. Observations indicate near flatness over the visible region and no detected small repeating topology. They do not provide a complete map of all space. Different possible global shapes can share the same local observations for a long time. A very large finite universe and an infinite universe may look nearly identical from within a limited observable patch. The same galaxies, background radiation, and redshift patterns could appear in both if the local geometry and expansion history match. This is why the question of total extent remains open. The universe may be infinite, or it may be finite without an edge. Current evidence does not require a boundary where space ends. It also does not reveal any surrounding physical arena into which expansion occurs. The word shape can also mislead if it suggests viewing the universe from outside. In cosmology, shape is not a photograph of the universe as an object in a larger space. It is a description of the relationships among distances and paths inside the universe. Curvature can be measured by how light travels and how patterns appear across the sky. Topology can be tested by searching for repeated structures or matched patterns. These are internal tests. They do not require observers to stand beyond the universe and look back at it. The possible global shape also connects to the early history of expansion. The observed near flatness is one of the reasons many cosmological models include a period of very rapid early expansion called inflation. Inflation is a proposed early phase that could make the observable region appear extremely smooth and flat. Many versions of inflation exist, and evidence supports some broad predictions, but the detailed mechanism remains uncertain. This uncertainty is stated carefully. The near flatness is measured. The exact cause of that near flatness is still part of active research. At this layer, the answer to the expansion question becomes broader but not more speculative. The whole universe may be larger than the visible part by an unknown amount. It may be infinite. It may be finite without an edge. Its global connection may be simple or more complex. Observations strongly constrain some possibilities and leave others open. None of the supported descriptions requires an outside space in the ordinary sense. Expansion is still the change of scale within the universe's geometry. The calm picture is one of measured limits and open possibilities. The visible universe appears very close to flat. No edge is observed. No central point is observed. No surrounding container is observed. The total shape remains uncertain because light has reached observers only from a finite region. Yet the uncertainty does not turn the outside into a required place. It only marks the boundary between measured knowledge and unknown global extent. Whether the universe is infinite or finite without an edge, expansion can be understood from within. The distances change, the light stretches, and the geometry carries the meaning without needing an outer room. At the innermost point of the question, the idea of an outside becomes the object of attention itself. The question asks what space is expanding into, but the scientific answer does not point to another place beyond the universe. It points back to the meaning of space. In modern cosmology, space is not treated as a material object moving through a larger room. It is part of the physical structure in which distances, directions, and paths are defined. When space expands, the distances between far, unbound regions increase. The expansion is a change within the universe, not a motion of the universe into an external emptiness. This answer is quiet because it removes a familiar picture rather than replacing it with another ordinary picture. Human thought is trained by objects. A cup sits on a table. A cloud spreads through air. A flame grows in a room. A wave crosses water. In each case, something expands into something else. The surrounding space is already there, waiting to receive it. The universe does not fit that pattern. It is not known as one object inside a wider container. It is the whole setting described by physical law. Asking what it expands into can therefore be like asking what lies north of the North Pole in ordinary geography. The wording carries an assumption that stops being useful at the boundary of the concept. The expansion of space is measured from within. Distant galaxy light is redshifted. Ancient background radiation is cooled and stretched. Large-scale patterns preserve rulers from the early universe. Supernovae and galaxy surveys trace how distances change with time. None of these observations requires a view from outside. No measurement shows an outer wall, an advancing surface, or a surrounding void into which the cosmos pushes. The evidence concerns relationships among places inside the universe. It shows that those relationships change as cosmic time passes. The word into suggests a direction beyond space. In ordinary motion, a direction is defined inside space. A planet moves around a star. A photon travels along a path. A galaxy falls toward a cluster. These motions occur within the universe and can be described with distances and directions. If space itself is the setting in which directions are defined, then an outside direction is not automatically meaningful. It may be possible in some mathematical theories to describe higher dimensional settings, but observations do not require such a setting for standard cosmic expansion. The established description works without it. General relativity gives this answer its formal shape. The geometry of space and time can change. Matter, radiation, dark matter, and dark energy influence that change. A scale factor describes how large-scale separations evolve. The universe can be described as expanding if this scale factor grows. Nothing in this basic description demands a surrounding arena. The mathematics concerns distances measured within the universe. It does not add an external space unless a separate theory calls for one, and such additions remain beyond what is required by the main observational evidence. This does not mean the universe expands into nothing as if nothing were a hidden substance. Nothing is not a place. It has no distances, no directions, no clocks, and no boundary. Saying that the universe expands into nothing can mislead if it suggests a dark, empty region outside the cosmos. The more precise statement is that the expansion of the universe does not need an into. Space expands in the sense that distances within it increase on large scales. The word into belongs to ordinary objects in ordinary surroundings. Cosmic expansion is a property of the surroundings themselves. If the whole universe is infinite, expansion still does not require an outside. An infinite universe can have its scale increase everywhere. The distance between widely separated regions can grow. While the universe remains infinite, it does not gain a border. It does not occupy more of a larger emptiness. If the whole universe is finite without an edge, expansion also does not require an outside in the physical sense. A finite space can grow in its internal distances without having a boundary that belongs to the space itself. In both broad possibilities, the same central point remains. Expansion is internal to geometry. The observable universe adds another layer of restraint. Observers can see only as far as light and cosmic history allow. Beyond the horizon, there may be more universe, perhaps far more than can ever be observed. That beyond is not an outside of space. It is beyond the current reach of signals. The horizon is a limit of information, not a wall. The unknown global extent of the universe does not create a known external container. It marks what present observation cannot settle. The early universe also does not require an outside. The hot, dense beginning described by the Standard Model is not an explosion from a point into empty space. It is an earlier state of the whole observed region, when distances were smaller, temperatures higher, and matter and radiation more densely packed. Every observed direction leads back toward that early hot state. No direction points back to a central launch site, the beginning of expansion, as far as current physics can describe it, is not a place in space. It is a condition of space and time. There are still uncertainties. The complete nature of dark energy remains unknown. The exact earliest moments of the universe remain beyond tested physics. The total size and topology of the universe remain unsettled. Quantum gravity, a theory that would combine quantum physics with gravity at the deepest level, is not yet complete. These open questions are real. They do not, however, change the core answer supported by current cosmology. The observed expansion does not require ordinary space outside space. It is described as the growth of distances within the universe. This inner answer can feel spare because it denies the imagination a surrounding room. Yet it is also stable. It is built from measurements, not from the need for a picture. The universe expands because light, distance, structure, and time all show a changing scale. The expansion has no observed center. It has no observed edge. It has no measured exterior. It does not behave like smoke spreading into air or a sphere swelling into a chamber. Those images belong to objects within space. The universe, in this description, is the space in which such objects and images can exist. The final form of the answer is therefore simple and careful. Space is not expanding into another known space. Space is expanding in the sense that the large-scale distances within the universe are increasing. The word into is not needed by the physics, and no observation supplies the missing container. What exists beyond the observable horizon remains uncertain, but it is not identified as an outside room. The universe carries its expansion in its own geometry, in stretched light, in cooled ancient radiation, and in the widening separations of unbound regions. At the innermost point of the question, there is no outer room waiting beyond the edge. There is only the universe, measured from within, changing its scale. The question becomes quiet at the end of the path. The farthest light, the ancient glow, the web of galaxies, the empty voids, the bound clusters, the local group, the solar system, and the small instruments on Earth all point toward the same careful meaning. Expansion is not the motion of the universe into a larger chamber. It is the changing scale of distances within the universe itself. The mind may still reach for an edge, because ordinary things have edges. A stone has a surface, a cloud has a shape, a wave spreads across water. The universe does not need to follow those familiar patterns. Its expansion is known through redshift, through cooled radiation, through measured distances, and through the large structure of matter. These signs are read from inside the universe, by observers who are also part of it. No telescope shows an outside room. No observation finds a wall where space ends. No direction reveals a center from which all things flee. The evidence remains gentler and more exact. Far regions become more separated when they are not bound by gravity. Light stretches as it travels. Ancient warmth fades into a cold microwave glow. Local systems remain held together, while the wider geometry changes. What lies beyond the observable horizon remains beyond present signals. It may be more universe, perhaps far more than can be seen. Its full shape remains uncertain. Yet this uncertainty does not require an exterior. It only marks the limit of what light has delivered so far. So the answer rests in a simple form. Space is not expanding into something known. Space is expanding as the distances inside it grow. The universe carries this change within its own geometry, without a visible boundary, without a central point, and without a surrounding room.